Hello, today we're going to take a look at state-driven game agent design. This is an article from the website AIjunkie. It's quite an old article, but they go through a nice way to do basic AI behaviors. What we're going to do is we're going to take what they have done and convert it into C# and apply it in Unity to get some nice harvester behaviors. What we're going to do is we're going to have a harvester that can move between a base and a resource and gather resources basically. They use something called finite state machines, which they go into some detail on the article itself, which I will link you to in the description. This is the code that we're going to be converting. It's just that little section over there. So we're going to take that, put it into Unity, and see if we can get some nice harvesting behaviors going. This is what our finished product will look like. We have the blue little cube harvester going between the resource, the yellow sphere, and the red cylinder over there. So it just goes, gathers resources, takes it to base again, and that's it. So it looks simple, but it applies the finite state machines, and it enables you to easily expand on this to add your own behaviors. It also has an evade. Let me just grab the enemy so I can show you how that works. Let's drag this guy near to the harvester, and you'll see that when the harvester sees the enemy, he runs away from it until the enemy is or until he's out of the range of the enemy, and when that happens he goes back to harvesting again. So we're going to look at how to do these kinds of behaviors inside Unity. Let's take a look at this state-driven game agent design in a little bit more detail, specifically regarding the finite state machines. So they've been used for a very long time in AI to get simple behaviors. This is because they are quick and simple to code, very easy to debug, which you'll see later. They have little computational overhead, which is always a plus anytime you're doing games programming. They are intuitive, so it's very easy for you to think about the states and how things change between these states. And they are flexible. It gives you nice flexibility, and you can easily change the behaviors and add new ones as you desire. What is a finite state machine? Okay, they go through a bit of the history behind it in the article, which you can read through, but basically it's all about having things in states and switching between those states based off of inputs. So the example they give here is just a light bulb, where the light bulb can either be on the on or the off state, and the transitions between these states are created by either flipping the switch down, which changes from the on state to the off state, or flipping the switch up, which changes from the off state into the on state. Now of course the behaviors in things like games are much more complex than that, and they go through a few examples here as well. They look at the ghosts behavior in Pac-Man. So if you look at how the ghosts behave in Pac-Man, there's one evade state. So all the ghosts evade in the same manner, but each individual ghost has its own chase state. So they don't all chase you the same way. And the input for this system is the player eating one of the power pills. So as soon as the player eats one of the power pills, all the ghosts transition from chasing to evading. And then the input of a timer that runs down is the condition for the transition from evade back to chase again. So that's a nice example of using finite state machines to achieve behaviors. They also go through a few others, the Quake style bots, players in games such as FIFA 2002 they show here, which shows you how old the article is. The NPCs in real-time strategy games. So all these things can use finite state machines to achieve their behaviors. Then they go on to the implementation. I should say first of all, this implementation, which uses switches and if-thens, is the naive approach, which they do say somewhere in the article at the bottom. But this is just a good starting point for us. Once we've done this, the naive approach, we will then look at going into the more, well, the better way of doing things later on. Okay, so how do we go about this? The key thing they describe here is the state transition table. The state transition table keeps track of your states in the left hand column, the condition, which is what is going to enable the transition of the state, and the state transition on the right hand side column, which is the state you're going to go to when the condition is met. So the example they have here is they have the runaway state. So in this state the unit is running away. The condition you want to check for, you want to see, am I safe? If you are safe, you want to then go into the patrol state. If you are attacking and you are weaker than the enemy, you want to change into the runaway state. So this is how it works. You have your current state, the condition you're checking for, and when that condition is true, you change your state into the state transition column. The other ones are patrol. If you're patrolling and you are threatened and stronger than the enemy, you want to attack the enemy. If you're patrolling, threatened and weaker than the enemy, you then want to run away. So this is a nice little example for something like a security guard in a game, which patrols and attacks or runs away from enemies as is determined by well, these two functions, which you'll see later: stronger than enemy or weaker than enemy. What we're going to do though is we're going to be making a harvester. So we're going to have to construct our own state transition table for our harvester. Okay, so before we start filling in our state transition table, it's a good idea to start writing down what states we actually want to have. So obviously the first state we're going to need is the actual harvesting state. We want to be able to harvest the resources. We also need to have an evade state. And that's pretty much it for now. We're going to start with just the two states, harvesting and evading. Then we just need to think how we're going to transition between those two. So we're going to need to look at the conditions that we're going to check for. So current state, let's start with the harvesting state. Okay, while we are harvesting, if we are threatened by an enemy, we need to change our state into evading. Okay, so what condition are we going to check for there? We're just going to say if we are threatened, then we need to evade. Then if we are evading and we need to check for some condition for us to go back to the harvesting state. Okay, that condition is when we are deemed to be safe. So we're going to check if we are safe and we are evading. Well, if we are evading and we are safe, we need to go back to the harvesting state. If we are harvesting and we are threatened, we go to the evade state. So it's very simple with just the two states, but this basically covers it. Obviously this gets a lot more complex the more states you add, but the state transition table will help you very well for that. So think about if you want to attack or do any other kinds of behaviors, all those states need to be added into the state transition table. And then when you do that, you just need to always make sure that if you have a state on the left hand side, there must be a way to get to that state. So that state should exist in the right hand side. So for example, we have evade on the left hand side, there must be a state transition on the right hand side column that moves us into the evade state. Okay, let's get into some implementation. Okay, what you will need in order to do this is the following. You'll need a terrain, you'll need a unit that you're going to control with your state-driven design. You're going to need something to use as a base and something to use as a resource. Now on the unit, I'm actually assuming that you have a way for your units to move. That's hopefully why you're watching a video on how to do some behavior type stuff. That actually assumes that you've already got the basics of moving your characters around sorted out. So you're going to need all that covered. I am actually using the player motor and player controller from the Brackeys Tutorials. He does some very good stuff. I will link you to that in the description as well. So I just basically took the player motor and player controller from over there. that's what handles all the movement of these characters specifically. But what we're doing at the moment is we're just adding a new script to our object, because we're going to try to just convert that code from the AIjunkie website into C#. So this I'm just going to call behavior. Oh, maybe I should spell it properly. BE. Okay, new C# script. We're going to add that to our little harvester, and we're going to open that up in Visual Studio. Then we're just going to copy and paste this code. And then we need to paste it into our new behavior script. It doesn't paste very nicely, but that's fine. We'll fix that later. So basically what we're going to be doing is removing all the errors, so this will run with no errors inside of Unity. To start with, we have here, okay, let's look at the first line. We have an enum called state type. So this is just creating a little type that's going to keep track of all of our states. Okay, they have 3 states. They have runaway, patrol, and attack. That's from their example. We're only going to have 2 of these. We're only going to have evade. We're going to call ours evade, and we're going to have a harvest state. Just those 2, so we can delete the extra 3rd state over there. Then they have the function that actually updates the state of the unit. So they have update state and receives a state type called current state, and based on whatever the unit's current state is, it switches inside the switch statement. And so depending on if it's run away, it actually executes the running away behavior. That does the conditional check there. So if we are safe, it then changes the state to patrol. Inside the patrol case that they're checking for, it calls the follow patrol path function. So that's the function that would then actually do the patrolling. Then we check if we are threatened. If we are threatened, we do some more checks. We check, are we stronger than the enemy? If that is the case, we change the state. You'll notice this function also doesn't exist, so it changes the state to state attack. Otherwise, in other words, if we are not stronger, we are weaker, we want to run away. Then they had the state attack. If we are weaker than the enemy, there's another check they do, the condition. We change state to run away. Else, in other words, we are not weaker, meaning we are stronger. They have the bash enemy overhead function, which is basically the attack function. So what actually does the attack for your unit. Yeah, so obviously ours is a bit different to this, so let's start with this one. It's not going to be state run away, it's going to be state evade. So this is now giving an error because the compiler does not really know what state evade is by itself. You have to tell it that it's coming from our state type enum. So you have to say state type dot, and then you'll see it gives you all the enums over there. So we have the state evade and state harvest. So we want state evade in this case, and that gets rid of that error. The evade enemy function, of course, does not exist yet. We still have to make that. The check to see if we are safe or not doesn't exist, so we will need to make that. The change state function itself, as I said, does not exist, and the state we want to change to, according to our state transition table, is not state patrol, but rather we want to go back to the harvesting state. So it's going to be state harvest, and of course we need to say state type dot state harvest. Then they have state patrol, which for us is not going to be state patrol, it's going to be state harvest. Okay, what are we going to do here? Instead of follow patrol path, we will actually be doing the harvesting, and we're going to need to make that function. Then if we are threatened, again another function we need to make. If we are threatened, we're going to not check anything, we're just going to immediately change our state to the evade state. So I can remove all that. So we're not going to go to attack state, we're going to change our state to evade. So we can say state type dot state evade and break there, and we can remove the whole attack state. Okay, so that's a good start. Just missed this one. Use the state type here as well. And we can also obviously remove that part over there, and that's a good start. We just now need to create all these functions and make them return something so that we don't get errors. And I'm done. Okay, so I've just removed all those spaces, those annoying little blank lines as well. And these are all the functions that I've added. So we have just a void evade enemy. So this is where we will actually evade. Do the evading. Then we have the harvest function. I've just changed this name from harvesting to harvest, you might have noticed. So here we'll actually harvest things. There's the safe function. So here's where we will check if we are safe. And in the threaten function, we're going to see if I'll check if we are threatened. Just by default, the safe one is going to return false, and the threatened one is going to return true. Then here we have the beginnings of our change state function. Now this just receives the new state that we want to be in. So what we need to do inside here is make our current state equal to our new state. Okay, in order to do that, we need to have some way of storing our current state. So we need a variable to store that in. Just to do that, I'm just going to move this up from here to the top of our class. And then we're going to have our new state, or our current state variable. So we're going to have a state type variable called current state, and we're going to assign it a default value of state type dot harvest, because we want to start in the harvesting state. We don't want to start and just do nothing. We also want to see the state in the inspector, so we should make this public. It also allows us to be able to change states manually later, but as soon as you do that, you'll see that you get an error that says inconsistent accessibility. Field type behavior.state type is less accessible than field behavior.current state. So all that means is we need to change our state type enum to be public as well. So as soon as we do that, we no longer have that error. Yeah, I also think it's a good idea for us to maybe print to console what we are doing, or what our unit is actually doing. So just inside the harvest and evade functions, we're just going to use a debug.log, and inside the evade enemy, we're going to say evading, and inside harvest, we're going to say harvesting. Okay, so this will just fill up our console with messages at the moment. I'm just going to save that, and then let's just check if we've remembered everything, or if I've remembered everything, which is probably not the case. So let's check evade enemy, log, harvest log, change state. We never finished the change state function, so we need to make our current state equal to the new state that we receive here. So we just need to add current state equals new state. Okay, so that should make the state change actually happen, and I think that should be fine. Let's see, and here you'll see that I have disabled the working script. This is the working script over here. This is our new script over here called behavior, and let's see what happens when I run it. Okay, so let's see, let's look at the top again. Is it harvesting once and then evading for eternity? Let's see why that is. So it ends up in the evading state. So we start in harvest, we do the harvest function, we check if we are threatened, and threatened returns true at the moment, meaning that we will change our state to evade. And then inside the evade, when we are in the evade state, we do evade enemy, we check if we are safe. So let's see what that one does. Safe returns false. So because safe returns false, meaning we're not safe, we're not going to go into the harvesting state. So just to recap, safe is returning false. So if safe was returning true, that would mean that we are safe and we should go back to harvesting. But that's not the case. So safe returns false and nothing else happens. We just keep on evading the enemy. So that's why we have the never-ending message of evading. So basically that means it's working. We just need to now actually flesh out all our functions to get our unit to actually do the behaviors. Here we are going to start with the harvesting section. So we're going to need some variables to help us out to get the harvesting behavior to work. We have a public transform base location and a public transform resource location. So these will obviously store the location of our base and the location of our resource. We also then have a boolean variable called toResource. What this is going to do is just to keep track of which direction we are moving in. Okay, so let's take a look at the function. I've just added the code in here so long. So this is the harvest function. We're checking if toResource. Now remember, this is just to keep track of, are we moving to the resource or are we moving to the base? So if toResource is true, we're going to be moving towards the resource. If it is not true, we then move towards the base. Okay, so here we're just using our motor. I've also had to add that. So we need an instance of our player motor over here, to a reference to our motor. This is what allows us to actually move our unit. We also need to add another line there. I'll do that just now. But for our harvest, okay, if you're moving towards the resource, we say motor.move to point, and we need to give it the location that it's moving towards. In this case, it's the location of our resource. And we have an if statement. We're just checking if the distance between our position and the resource location is smaller than a value. I just use 2. We should actually probably just make this a variable, but for now our little hard-coded 2 is fine. So as soon as we're close enough to our resource, that's what our goal was, just to get to the resource. As soon as we get there, we can change toResource to be false, which means that the next time we come to our harvest function, this will be false, and we will then be able to move towards the base. So to do that, we just say motor.move to point, and we now give it the base location instead of the resource location, and it will then start moving towards the base. Then we do the same distance check again. We check to see if the distance between our position and the base's position is smaller than 2. We then make toResource true again. So this might not be the most efficient way to do it, but I think it's very easy to read and to understand how this will affect the unit. So once we have this in place, the harvesting behavior should work. Now for us to test this, we should probably just make ourselves safe all the time, so that we will stay in the harvesting state and not go into the evade state. Let's save and see what's happening when we run the script now. We get an error because I forgot to instantiate our player motor. Okay, so to do that, just need now in our start function, I just need to say motor equals get component player motor, and that should do it. Save that, go back to Unity and hit run. We also need to, of course, assign the resource location and base location transforms over here. So base location and resource location, we just need to drag our base into the base slot and our resource, which is that sphere over there, into the resource location slot. And now when we run, hopefully it will do things, and there you go, it's moving to the resource, back to the base, and back to the resource again. Okay, so now we can start with our evade state. It's a little bit more involved than it was to do the harvesting state. So for us to do our evade behavior, we need an array of game objects. This will be used to store all our enemies that are in the scene. We also need to store a single game object. In this case, it's called enemy to evade, and this will be the enemy that we are currently evading. We also then just need a transform, basically, or vector 3, where we're going to go when we actually do the evading. And then over here we have a public int threat range, so how far away we can detect a threat. So the bigger this number is, the bigger the range of detection is. So if you have a range like 10, we'll have a massive radius where we check for enemies, and if there's any enemy inside that radius, then we will start to evade that enemy. The smaller, of course, the smaller the radius gets. To get to our evade state, at least we need to get there from the harvesting state by achieving this condition, or triggering the condition of threatened. So let's take a look at how that works. Threatened function over here checks if we are threatened, and how this works is we use our enemies array of game objects, and we assign to that game object.find objects with tag. So what this does is it finds all the objects in the scene with the tag of enemy, and it stores them inside enemies. Then we're just going to loop through that array. So for each enemy inside our enemies array, we do the following check. We check, is the distance between ourselves and the enemy smaller than the threat range that we declared above as 5. So if the distance between ourselves and the enemy's position is smaller than the threat range, that means we are threatened, and we need to then actually evade the enemy. So enemy to evade will then be that enemy, the current enemy that we're looking at inside our enemies array. So we need to assign that over there, and we're just going to pretend that you did not see that line over there, because this is actually done somewhere else. So what's happening here is we just set the enemy that we're going to evade, and we return true. So function return true. So while we're in the harvesting state, threatened returns true, meaning that we'll change our state into the evade state, and now we should be in the evade state. And that will of course then actually call the evade enemy function, which looks like this. So we still have that evading message over there in the console, and we are assigning to our run to location. Remember, this is where we are going to evade to. This is a very basic evade behavior. All it basically does is it moves, tells our unit to move 12 units in front of our enemy, wherever the enemy is facing. So let's just go through how this works quickly. So we look at the enemy to evade. This is the enemy that we are currently evading. We look at its position and we add to that same enemy's forward position multiplied by 12. So we just add a value to the enemy's forward so we just add a value to our enemy's forward transform and store that inside our run2 variable, and then we need to actually move towards that location. So what this does is it makes it so that our harvester always moves to a location that is in front of the enemy, so it makes it look like it's running away. It's not the most intelligent evade behavior, but it works just for what we're doing now. Okay, let's take a look and see if this is working. Did I save that? Yeah. No, I did not. Let me save, and we go over here and click run. Okay, so we have our unit harvesting over there, and if I just bring in the enemy, where's my enemy? There he is. Drag him in a bit closer. Okay, he's chasing the harvester. Is the harvester running away? Yes, he is. Okay, so as you can see, he's always running to a location in front of the enemy. So even there, he could have run past him, but he keeps going 12 units in front of our enemy. Okay, we also, just like how we have a threaten section, we also need to do the safe function, which is checked over here. So if we are safe, then we need to go back to our harvesting state. So to do that, it's very similar to our threatened function. Again, we have an array, or we use our enemy's array. We assign to that any object with the tag enemy, and we loop through the array for every enemy inside enemies. We check the distance between ourselves and that enemy to see if it is smaller than some range. It's just a hard-coded 12 in this case, and if that is the case, if it is less than 12, we return false, meaning that we are not safe, and if that does not happen, we will then return true, meaning we are safe. So that's the safe section, or safe function. I do like to just have a little visual indication of what state the unit is in at the moment. It's easy to do when you're using little basic assets or no models like what we're doing now. So I'm just going to change the color of the unit depending on what state it is in. So if we are in the evade state, I'm going to change the color to be yellow. We do that by saying get component in children mesh renderer .material .color. Allows us to access the actual color of our cube in this case, and we say color .yellow. That just makes it yellow when we are in the evade state, because yellow is the color of cowardice, so that kind of makes sense. When you are harvesting, we're probably just going to leave it as red at the moment. So it's going to be red when in the harvesting state and yellow when evading. Yeah, let's just see what that looks like. Okay, so that stays red at the moment. Then when I move the enemy in closer, should probably have made this easier for myself to do. Okay, so as I move the enemy in closer, you'll see the harvester changes color to yellow, and once it's out of range of the enemy, it becomes red again, meaning it's trying to harvest again. Still being chased. The enemy, by the way, wanders, and if it encounters the player or anything on the player side, it then attacks and shoots at the player. So this is of course its own finite state machine, and it's hopefully the kind of things that, or kind of behaviors that you can apply when using state driven design. So this guy just wanders around, and shoots at things that he finds. So hopefully this will help you in your future creations. And maybe in the next video I'll look at the non-naive approach to do state-driven design.